How do I? Hey, how do I see everyone now? Can you see the screen?
Yes,
Hello?
sir.
Yeah. Okay. I think maybe we can start, right? In the last class, we started looking at what a Poisson process is, right? That's what we started looking at. So, what is a Poisson process? Yes, what is a Poisson process?
It's a process like the interarrival times are exponentially distributed.
Inter-arrival times are exponentially distributed. Is that enough?
It's the renewal process also.
Yes, right. That means, what do you mean by that? The inter-arrival times are independent. That means it's a renewal process. And then the inter-arrival times distribution is exponential. Right? Is that fine? So that's about the Poisson process. So then we also saw a few properties of a Poisson process. What were those? What were those?
Memoryless property like interarrival times.
So it's memoryless, and then okay, and what else? So we saw a few things, right? Suppose I say that until time t, the nth arrival hasn't happened. Okay, n minus 1th has happened, but n minus nth arrival hasn't happened. Then if I ask what is the probability, if I look at the distribution of the n plus nth arrival from that point t, then that is independent of what happened before, right? That is something that we looked at. Okay, so we proved a theorem along those lines, and we started with a few definitions, right? We'll continue with that today. So we started looking at what is known as a stationary increment, right? So a counting process. What is a counting process? This one, right? This is a counting process. It counts the number of arrivals, right? Has the stationary increment. Property if you look at n of t dash minus n of t, I think I wrote this in the last class, but I'll rewrite it. So if you look at n of t dash minus n of t, what does that mean? N of t dash essentially says that there are n of t dash number of arrivals from in the time interval 0 to t dash. N of t is basically says the same thing. So if you look at the difference, has the same CDF as n of t dash minus t, okay, for every t dash greater than t greater than 0, right? So pictorially, what does it mean? So suppose you look at this is 0, this is t, and this is t dash. Okay, now if you look at the number of arrivals in this interval, for example, if you look at how many people arrived in this interval, this is what this is basically n of t dash minus t, but I can write this as n of t dash minus n of t, right? So that gives me n of t will tell me the number of arrivals at time t until time t. N of t dash will tell me how many people arrived until time t dash. If you look at the difference, it tells me how many people arrived in the interval t to t dash. Okay, so now it's a the definition is saying that this difference should be same as n of t minus t dash. That means you look at the interval difference, right? Interval t to t dash, or this difference t dash minus t. This is t dash minus t. Yes.
So that means only arrival is allowed. No person can leave.
No, I'm just looking at a person can leave, they can do whatever, but I'm just looking at the arrival process. Of course, I can also look at the departure process, right? I can, instead of arrival, I can change it to departure. There's no harm in doing that.
I mean, sir, the counting process in n of t, it considers only arrivals, or it considers arrivals and departures like aggregates, like.
No, 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 no. So it just considers arrivals or departures, one of them. Okay. Yeah. Is that fine? Is that fine, Rishabh?
Yes, sir. Yes, sir.
So you can also have, let's say, T1, T2, but the difference turns out to be T dash minus T. Okay. T dash minus T is same as T2 minus T1. So if you look at the arrival here, let me call this as N T2 minus T1, right? Or to be very specific, it will be NT2 minus NT1. Okay. So the distribution of this is same as distribution of this, which is same as distribution of this. So essentially it says that it doesn't matter at what time or at what time point are you looking at, it essentially depends on the time difference. So that's why it's called stationary increment. You can shift this interval T1 to T2 to any time, anywhere in this x-axis, and ask the question of how many people arrived in that interval. The statistics remain the same. It's not going to change. Okay. It means from 10 o'clock to 11 o'clock, if you count the number of cars arriving at, let's say, a junction, it doesn't matter which day you look at. As long as you look at 1 hour window, you look at today afternoon, or today evening, or day after tomorrow afternoon, it doesn't matter, right? That's what it says. If the arrival is stationary increment, right? Is that okay? Understood this concept? Yes or no?
Yes, yes, sir.
Okay. So let's move on. The second thing that we looked at was the definition of independent increment property, right? Again, a counting process. This, which is n of t, t greater than 0, this is a counting process, has independent increment property. If you take an integer, right, for every k belonging to let's say n natural number, and k tuple of times, and k times, okay, so let's say 0, t1 less than t2 less than so on less than tk. Okay, you take k arrival instance. Okay. Then you look at n of t1, that is the number of people arrived until time t1, number of people arrived who arrived in time interval t1 to t2, and so on, number of people who arrived at time tk minus 1 to tk, or statistically independent. Independent. Well, what is the immediate consequence of this? we can immediately say, based on previous theorems and discussions, that Poisson process has stationary increment property as well as independent increment property, right? Or Poisson induced counting process.
Sir,
Yes.
sir, like the thing that we agree on n t1 t2 and up to tk minus
So
1
I
tk.
think yeah.
Sir,
I
this
can.
has this tuple has to be like the immediate, like the t1 t2. It cannot be t1 t3 or like something like that.
No, if there is an overlap, then it need not be independent, right? Do you agree?
Yeah.
So if
So
I
my
ask, yeah,
so
go
my
ahead.
question is that like
Hmm.
n t1 t2 will not be equal to n t1 t3. That is the question.
And T1, T2?
Will be equal to n t1 t3 or not equal to n t1 t3?
No, it need not. It need not be. See, NT1, T2 will be equal to NT1, T3 provided NT2, T3 is 0, right? Nobody arrived in that interval. Is that fine?
Yeah, okay.
Right? Somehow it got, I don't know why. Okay, this is fine. This whole thing. So this essentially based on our previous discussion, etc. It implies that if you look at a Poisson process, Poisson processes have both what stationary increment property okay as well as and what independent increment property, right? Okay. Okay. So
Sir,
before,
these two,
yes.
so these two properties kind of similar. It sounds similar. I don't know.
One essentially says that the if you look at any interval and ask how many people arrived in that interval, the statistics of that remains the same even if you shift that interval to any point on the real line, right? That is that's what stationary increment property says. So it only talks about the statistics. It doesn't say whether it has to be independent or not.
So is it kind of identically distributed? This statement is, and the next is independent.
Yes, exactly. One is identically distributed, the other one is independent. Exactly.
Okay.
Okay. So put together, you can say that it should be an IID process. Okay. Okay. Is that fine? So
Yes, sir.
before going to dealing with this further, let's look at let's play around with the Poisson process. Okay. So we say that X is Poisson with rate lambda if I look at the PMF, right? So Px of k, this will be lambda power k over k factorial into e power minus lambda, and k is 0, 1, 2, etc. And lambda is positive. Okay. So clearly, if you look at this, right? So k equal to 0 to infinity. Of course, e power minus lambda I'll pull out. Lambda power k or k factorial. What can you say about this? I'm just
It's
summing
e
the
to the power
Poisson.
lambda.
Huh?
E to the power lambda only, sir.
Is this e to the power lambda?
No, total will be the 1.
Okay, yeah. So this will be because this is nothing but e power lambda, right? This is very clear. Okay. So it sums to 1. The second thing is let's look at expected value of x. So what is expected value of x? Again, k equal to 0 to infinity, k e power minus lambda, lambda power k over k factorial. So What can you say about this? Yes. What can you say about this? How do you compute this guy?
Sir, just expand it. There will be a cancelling by k. Then we have to take a lambda common.
Okay, so let's do that. E power minus lambda k equal to 0 to infinity. Okay, so I'll just do the following. Okay, so I'll just take k minus 1 and pull a lambda out. Okay, divided by k minus 1 factorial, because this k and this k factorial cancels to get k minus 1 factorial. Is this fine?
Yes, sir. So here
Now,
k will be from 1, I think, no?
so you cannot have k equal to 0 to infinity. So this is lambda e power minus lambda k equal to 1 to infinity lambda power k minus 1 or k minus 1 factorial. Okay, this is lambda e power minus lambda. This is same as summation
Throw
k equal
lambda.
to 0 to infinity lambda power k or k factorial. This is nothing but lambda, because the summation will be e power lambda, and that cancels with e power minus lambda to get lambda. So we know that the average of the Poisson is lambda. Okay, so what can you say about this guy? Let's do the one more calculation. What can you say about this? K equal to 0 to infinity k squared e power minus lambda lambda power k or k factor. What can you say about this? Okay, let's do the same trick again. Let's see what will we get. 0 to infinity k cancels. Okay, so we have k lambda power k minus 1 over k minus 1 factorial, and there is a lambda. Okay, now what do you do?
So this one we have already calculated above, I think.
Did we calculate this? See, when k is 0, it doesn't matter, right? So this starts from k equal to 1 to infinity k lambda power k minus 1 over k minus 1 factorial. Now how do you solve this guy? Right? How do you solve this guy?
K minus 1 equal to V, some put
Huh?
V equal to K minus 1, and then
What is that?
so let's assume K minus 1 equal to V. Then we can change the limit and
Okay, let's do your approach. So lambda e power minus lambda. You are saying I'll call k minus 1 as, let's say, L, right? When k is 1, L is 0, right? So I should start from 0 to infinity. What happens to this thing? So we can do that, right? So L is equal to, see, when k is 1, L is 0. When k is infinity, L is infinity. So let's do this. L is k minus 1. So k is L plus 1. This will be lambda power L over L factorial. Is that okay?
Yes, sir. Okay.
Now what do you do?
Just multiply and
Okay, so let's do
separate.
that. E power minus lambda. The first term will be L equal to 0 to infinity L lambda power L or L factorial. The second term would be summation L equal to 0 to infinity lambda power L or L factorial. What is this? Lambda e power minus lambda. What can you say about the first term? L equal to 0 to infinity L lambda power L or L power. So this is something that we computed here, right?
Yes.
Exactly here, right? So what do we get?
Lambda. Sorry, L.
No, lambda e power minus lambda. E power lambda, right? This will be lambda e power lambda. Right?
Yes, sir.
plus e to the power lambda.
Plus this will be e to the power lambda. So what do you get? Lambda times e power minus lambda and e power lambda cancels 1 plus lambda. Do you agree?
Yes,
Okay,
sir.
so now this is the second moment of a Poisson arrival. So it's of the order of lambda squared. Okay, depends on the square of the arrival process, arrival rate. Okay, which makes sense. So now, what can you say about the variance of x? So do you agree that the variance can be written as expected value of x squared minus expected value of x whole squared, right? So this is same as expected value of x minus expected value of x whole squared, right? That's the variance. Is this fine, everyone? This one is fine,
Yes, sir.
right?
Yes.
What is the expected value of x squared? I know, right? Lambda plus lambda squared minus, what can you say about expected value of x,
Lambda square.
right? Is this fine? Is this correct? I hope so. The
Yes, sir.
second moment,
Yes, sir.
okay. Right, so it's easy to compute the moments here, right? So there are other ways to compute moments. For example, you have what is known as the MGF, right? How did we write MGF? I
Gx
think
of R.
huh?
So we have to use the notation Gx.
G, right? Gx
Yeah.
of R is
Or
expected value of
e to the
e
power
power
tr.
Rx,
Rx.
right? Now, how do you find the first moment here? So you take the derivative of this, okay, with respect to r. So what do you get? This is expected value of x e power rx. Okay. Now substitute r equal to 0. What do you get? Did I
Expectation of x mean.
did I do this when I discussed moment?
Yes, sir.
Huh?
Yes, sir.
Okay, so anyway, so I'll just repeat one more thing. So if you look at gx double dash of r, what do you get? It's expected value of x squared e power rx. So this implies g double dash of 0 would be expected value of x squared. So that means you can compute all the moments and so on using the moment generating function. So that's why it's called moment generating function, MGF. So what you can do is, as a homework, you compute the MGF of a Poisson random variable, a Poisson distribution, and find a few moments, for example, third and fourth moment. Okay, that will be an exercise problem. Okay, yeah. So I think this is some computation that we need later on. Okay, it's good to know this kind of a computation. Okay, so now okay, so let's look at the arrival now itself, Poisson arrival. So what do we have? So we have this, right? So there will be an arrival here. This is at S1. There will be an arrival here, S2. There will be an arrival here, S3. There will be an arrival here, S4. There will be an arrival here, S5, and so on, right? And let's say there is an arrival at this point, which is Sn, the nth arrival. Okay. Now we have been instead of characterizing Poisson process as times at which an arrival happened, we characterized Poisson process as in terms of inter-arrivals, right? And independence across inter-arrival times. That's how we describe Poisson process. Now, suppose, now of course I know this is your x1, this is x2, this is x3, and so on, right? So instead of characterizing, so now I know the distributions of xi, which is exponential. Now I want to find, for example, the distribution of this time instance. What is this? Right? For example, this is the density of Sn, the nth arrival. So how do I find this? Any idea? So let's start with something simple. Don't look at the book. Let's start something with the simpler one. Okay. So what can you say about, for example, S2 of t?
The bit convolution of S1 and S2.
Yes.
So it's just convolution of the density function with respect to S1 and S2.
So let's look at it this way, right? So this is nothing but x1 plus x2, or I can write this as s1 plus x2, right? X1 is same as s1, right? Do you agree?
Yes,
So
sir.
that means I know s1 of t. What is s1 of t? Lambda e power minus lambda t, right? So this is s1 of t. Yeah, is that fine? This is the density of s1 of t, right? Okay. So how do you find s2 of t? What do you think is the answer? How do you find s2 of t? If you find s2 of t, then I can induct and find all the other expressions, right? So what do you think is s2 of t?
Sir, X2 of T is also same, I think. No, sir, because they are IID.
No, you also have an extra x2 here, right?
No, sir, I am just talking about only X2.
x2
Because
is
the
fine. x2 is exponential
yeah, this is also exponential, no, sir.
and independent of
So
s1. That's very
yeah,
clear.
yes, sir. So we have done earlier that if a X1, X2 are IID, then we can find the density of the Z is equal to X1 plus X2 just by taking their convolution.
Okay.
So
Yes,
in
you
that
can
way, I think
do the convolution. So, for example, I can write S2 of t as you said, it's convolution of x1 of t with respect to x2 of t, right?
yes,
Is
sir.
that fine? Right? This
Yes,
gives
sir.
me. So, what is the convolution? Can you try? Can you guys try and tell me what is the answer?
Uh,
Yes.
Sir, I have one question.
Huh.
Sir, every time when you need to find the density function, uh,
Uh-huh.
I don't know it is feasible or not. I mean, instead of convoluting, can you find the CDF and then differentiate it? Because you mentioned in the first or second lecture of question, like the SN less than T is also an event. So we can find the CDF and then differentiate and
Okay.
then get
So
the PDF.
okay, so let's try that first, and then you can try the one that I have given. Just give me one second. I'll just
Okay,
connect
okay.
laptop to the power supply. Okay, so yeah, so let's look at this. You fill the gap. Okay, so let's take the approach of whatever you are saying, right? Probability of S2 less than T. That's what you are saying, right? Do you agree? So
Yes,
this
sir.
is nothing but probability of S1, which is S1 plus X1 less than X2 less than T. Do you agree, Rishabh?
Yes, sir. Yes, sir.
I'm finding the CDF. Okay. So now, what is it that I have to do after this?
Both are IIT.
Yeah, both are IID. What is it that I have to do?
So we can
I
write
can do
S1 less than T minus X2.
T minus X2.
Then we know what is this
Given X1
probability of this
Hmm?
is CDF of S1 X1.
No. Okay. So now what is it that I have to do now here? S1 less than T minus X2, but I don't know what X2 is, right? I should condition on X2.
X2, yes, sir.
Well, I'll say this is little tricky. I'll write it like this, but it's not really a good idea because x2 equal to x2, right? That is an event of zero measure, right? It does not make sense. But intuitively, it essentially means that x2 can take a value around the small x2, let's say delta very small, and later we'll take delta to 0, okay? Times probability that x2, yes.
Sir, I think this will eventually end in convolution only.
Exactly, that's what I'm trying to,
So, sir,
right? Yeah, so this, but this is not equal to this, right? So I have to integrate this with respect to what? X2, right? 0 to infinity. Now, what is the next step, Rishabh? What is probability of this event conditioned on X2? So, well, I'll write one more step. So this is probability of S1 less than T minus small x2 because it takes x2, condition on x2 equal to x2 times fx2 of x2 dx2, right? So what can you say about this now? So S1 is less than some number given x2 is equal to x2. S1 is same as x1, right? So x1 and x2 are independent. So I can write this as
Yeah.
probability of x1 less than t into the density of x2.
So it is from memoryless property, right?
Which one? So memoryless means independent, right?
Yeah.
So x1 and x2 are independent. Is this correct? Did I make any mistake? No, right?
T minus x2, right, sir?
Yeah. T minus x2. Okay. Fine. So of course, t should be greater than x2, right? If x2, so this t is not, I mean, in this case, I'm saying t is greater than x2 or x2 is less than t. Okay. So that means I cannot just integrate, right? What should I do? From 0 to infinity, I cannot integrate. What should I do? See, if I start from 0, right, x2 is 0, it starts from t. x2 goes to infinity, this will be s1 is less than minus infinity. Minus infinity, well, that is 0, right? You can go at most till what? x2 can go up at most till
T.
right? Yeah. Okay, so now can you find this blah 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 blah, right? So it turns out, well, do you want me to do this? So this is what is this? This is nothing but 0 to t minus x2 lambda e power minus lambda x dx, right? So that is lambda e power minus lambda x by minus lambda 0 to t minus x2. So lambda cancels. It's 1 minus e power minus lambda t minus x2, right? And you have similarly 1 minus this, right? You have to substitute this here. What is this? This is lambda e power minus lambda x2, right? And then multiply and integrate. This is nothing but convolution. Okay, fine.
Okay, sir. Okay, sir.
Okay. Is that fine, Rishabh? So essentially, I want you to fill this gap, which is nothing but the gap here. You have to find this integral. That's all. Okay. So both are same, and then take the derivatives. So here you have to take the derivative. Finally.
Yes,
Okay,
sir.
that is the only difference. So convolution, you need not take any derivative. You are convolving two density functions. Whereas here you are doing something more. You have to take the derivative as well. Hmm? Is that okay? I think Ayush, right?
yes,
You were
sir.
saying both turns out to be same, not same, very similar.
Yes,
Is it okay?
yes, sir.
Yeah. So now, what is it? What it turns out that fs2 of t would be lambda squared t e to the power minus lambda t divided by something, one factor. Okay. So it turns out if you generalize, right, if Sn of t would be lambda power n, t power n minus 1, e power minus lambda t, everything remains the same. So what should I put in the denominator? Any idea?
N
See, this is
minus
how I
1.
generalize, right? So lambda square for S2, so 2, so lambda n will be, Sn will be lambda power n. For S2, there is a t power 1 instead of 2, so that means n minus 1, so I put n minus 1. E power minus lambda t is independent of n, so I write that. So what should I put here?
N minus 1 factorial.
Huh?
N minus 1 factorial.
How did you find that?
Because for S2 it was 1 factorial. So
Well, how do you know that this is 1 factorial and not
no,
here?
you mentioned, so that's
No, it could be, for example, a power some number power n minus 2 also, right? But that's not the thing, right? So if I integrate, for example, this, right? So if I take the numerator and integrate from 0 to infinity, right? Lambda power n, t power n minus 1, e power minus lambda t dt. So this is something that I want to divide, because if I integrate density, I get 1.
So this
So
is
what?
gamma integration, right?
Huh?
This is gamma integration
Exactly. So what will be this? This is
from the
lambda power n 0 to infinity t power n minus 1 e power minus lambda t dt.
yeah,
Remember, this is not gamma, right? This is, I have to substitute for, let's say lambda t is s, then this will be lambda power n, okay, right? Is that correct? You have t power n minus 1 e power minus lambda t. So if you put lambda t equal to s, then what will happen to t power n minus 1? It will be by lambda power n minus 1, right? Is that correct? Everything fine, right?
sir. So in the previous integration, 0 to infinity t to the power n minus 1 e to the power minus lambda t dt.
Hmm.
So that comes down to gamma n upon lambda to
dt
the
is so dt is 1 by lambda ds. So this is nothing but this lambdas cancels, and you have gamma of n minus 1, which is n minus 1 factorial. Fine. So n minus 1 factorial is your normalization constant. Is that okay, everyone?
that. There should be gamma n, right?
Is it gamma n? Yeah, this is gamma n is n minus 1 factorial. Yeah. So this integral turns out to be n minus 1 factorial. You can check that. Okay. Is that fine? Clear or not clear?
Yes, sir.
Yeah, that's how you generalize, right? So you have this, but now you have to prove it, right? You have to prove that this is the density. Okay, so proof of the fact that I'll probably write it as a theorem. Okay, so you take IID x1, x2, etc. IID with distributed as fx of x equal to lambda e power minus lambda x, x greater than or equal to 0, and then you take let Sn is, this is, I'm just writing whatever, I'm just verbatim copying it from the textbook. So for n greater than or equal to 1, then this fxn or fsn of t is, right, for let's look at this. Okay, let's do this first. Let's look at the joint distribution of S1 through Xn. What do you think is the answer? Okay, let's fill. We'll start proving it, and once we prove, we will fill this. Okay. So now, how do you show that this is the one? FSN. Yes. How do you show that this is the one?
continuous convolutions.
Yeah, you do this, right? So you can follow the same procedure here, right? Instead of S1, you will have Sn, right?
S2.
And yeah, Sn being less than this, right? And you multiply it by the density of, so you condition on all the previous instances, right? So for example, Sn minus 1. Let's assume that it's true for Sn n minus 1. So That means if Sn minus 1 of Sn minus 1 is something that I know by induction. The only thing that I have to compute is Sn, right? So Sn less than something is what you have to compute, conditioned on the fact that Sn minus 1 is something. So if I know what is Sn minus 1, Sn is basically, you can assume that it's an exponential distribution, right? So that's how you compute this. Okay. Do you want me to do that? I'll finish this and maybe we'll come back to that. Okay. So how do you show this? Yes. What is if S1 S2 of x1 x2? Sorry, S1 S2. What is this?
Multiplication of marginal PDFs.
Yes, right. So no, not directly, right? So what do you think this thing depends on?
Sir, S1, S2 are not IIDs, right? They are not IIDs.
S1, S2 are not IIDs, right?
Yeah.
So what do you do? So I can write this in a slightly different fashion, right? S1 is nothing but x1, right? I'll call this as x1 and S2. Okay, is that fine? Now, although this is density, you can still have the base theorem, right? This holds good. So I can write this as f of S2 given x1 of S2 given x1 into fx1 of x1. You agree? Now, conditioned on x1, what can you say about S2? So let me write this. This is S1, okay? The first arrival, right? I'm talking about S2. This is the second arrival. S1 is same as x1. This will be x2. Okay. Now, if I conditioned on x1, right, that means I have conditioned on this guy. Okay, so let me use a different color. I condition on this guy. Now I'm asking what is S2? So what can you say about S2? Huh?
Greater than x1, that's all.
Huh?
Greater than x1.
Well, that is true, but
On
so this is x1 plus x2. That is something that I have, right? So I've conditioned on x1. That means this is given to be x1. Now, what can you say about S2? What can you say about S2? So this S2 given S1 would be what? Lambda, it's exponentially distributed. Lambda times, well, it's not really x2, but it's S2 minus x1, right? Do you agree? Why is this? Condition on x1, what is S2? S2 is basically x1 plus x2, small x2, right? So I better find the distribution of, I know the distribution of x2. So I use that, okay? So what will be this? This is e power minus lambda x1. So what is the answer? Lambda squared e power minus lambda S2. Well, it is independent of S1, which makes sense, right? Well, if you are looking at the joint density and if I know the recent arrival, it doesn't matter what happened before. Is this fine, or you got this from here to this thing?
No, sir. Can you please elaborate the thing that you are
Okay, so
using that?
let's look at this. Okay, so we want to look at f of S2 given x1 of S2 given x1. Okay, This is what I want. Okay, so let's systematically do it. So I'll take the approach Ayush said, right? So not Ayush, I think Rishabh said. So let's look at the densities. So let's look at the CDFs, right? So what is the CDF of this? So I should look at probability that S2 is less than something. Okay, so let me call this as S2 given X1.
X1 equal to X1.
So what happens to this? This is probability of S2 less than S2 is what? S2 is X1 plus X2 is less than S2 given X1. Right?
Yes, sir.
This will be probability of X2 less than S2 minus X1 given X1. Okay.
Yes, sir.
This is nothing but probability of X2 less than S2 minus X1. Why? X1 and X2 are independent.
Yes, sir.
So what is this? This is lambda. What is this? I have to integrate this from this is nothing
0
but
to
0,
infinity.
0 to not infinity. S2 minus X1.
Oh, sorry, S2. Yes.
Lambda e power minus lambda x dx. So what will be this? What will be this?
Lambda comes out.
Lambda and lambda will cancel. So you have e power minus lambda x with the negative sign 0 to S2 minus X1. So this will be 1 minus e power minus lambda S2 minus X1. Right?
Yes,
Now, I have to take the derivative to get the PDF, right? So this is S2 given X1 or S1. S2 given S1. So what is that? What is the derivative of this? It's lambda e power minus lambda S2 minus X1. That's what I wrote here, right? Right? Is this fine, everyone?
yes, sir.
Everyone got it? Rishabh?
Yes, sir. Yes, sir.
Yes, right? So it's easy. But it's useful to do it, okay? You should get used to these kind of computation. Okay, so now this is clear. So for 2 it is clear, right? So for 2 it is lambda square e power minus lambda S2. So what about n? What should I write here? Sorry, what should I write here? For 2 it's lambda squared e power minus lambda S2. Okay, let me write it here. For 2 it is e power lambda square e power minus lambda S2. What do you think the answer is for 3? 3 is lambda cube, naturally, lambda S3. So in general, this would be lambda power n e power minus lambda S n. Okay, is that fine? So this I will write. I think let me just change this. This is S1, this is S2, this is Sn. Okay.
Sir,
Yes.
so suppose we are calculating the same thing for the 3, means S3, no, sir. So in that case, sir, we have to condition on X1 and X2 both. Like,
Yes. No, the point is you have to condition on S2 and S1 both, but given S2 is independent of S1, right? Do you agree?
sorry,
Independent increment. See, condition on S2, it doesn't matter what happened before. You
oh,
agree?
yeah, sir.
That's the problem. Well, can somebody guess where are we heading when I said this? Well, I don't know why.
So the thing that we have claimed that bosons are the stationary independent
That is
something.
true, but I'm not asking you. I think others can. Okay, Ayush Agarwal, can you guess what is it that we are? Where are we heading? Ayush, are you there?
Like maybe we are trying to prove it is IID,
No.
like S1, X2 and all.
Obviously, S1, S2 are not IID, right? Why? S2 is definitely greater than S1, so that itself will bring in some correlation, right? It's not as simple as IID or independent. It's slightly more complicated. So when Sumit asked me the question, I said S3 condition on S2 and S1 only depends on S2. It doesn't matter what happened before, right? So why is that? Because Sn or S3 is S2 plus X3, right? S2 and X3 are independent because I'm picking X3 independently of everything from exponential distribution. So now S3 conditioned on S2 and S1 is independent of S1 and it doesn't matter, right? Is that fine? So where are we heading? It looks like something, right? It's Markov, right? Those who know what Markov is, it's conditionally independent. Given the immediate past, it's independent of all the what happened much before, right? Is that fine or no? Ayush?
Sir, is the interval times were designed like that, like interval times, the interval times in Poisson process, so that were designed like that, right? Like
Exactly,
the X3 or
exactly,
X4 doesn't depend before, doesn't depend on
exactly,
any.
exactly. Yeah. By construction itself, it turned out to be a Markov, right?
So I don't know Markov.
Okay, don't worry. So this is a very natural step. So first thing is IID. Second thing is independent but not identically distributed. Third thing is you bring in correlation but not too much, which is Poisson, like stationary Poisson. Then you look at non-stationary Poisson. That means you change the rate. Okay, and then you look for Markov. Okay, that's the natural approach. And once you look at Markov, you look at what is known as martingale. Once you look at martingale, you look at Brownian motion. Once you look at Brownian motion, you can, I don't know, you can describe, use some stochastic differential equations to describe some very complicated stochastic processes. Okay, that's the natural flow. Okay. Okay, so now we have proved this for 2, right? So induct on n. Okay, assume it's true for what? N minus 1. Okay, and then we'll prove, or it's true for n and prove for n plus 1. So this is what we'll do. Okay, so n equal to 2 is obviously true. We have, not obviously, we have proved that it's true. So now I have to look for Sn plus 1 of S1 Sn plus 1. What do I do? Well, same stuff, right? I'll take S1 through Sn of S1 through Sn times f of Sn plus 1 conditioned on S1 through Sn, Sn plus 1 conditioned on S1 through Sn. Okay, so this is very clear. S1 through Sn is basically lambda power n e power minus lambda Sn. Done. I only need to look at this thing, f of Sn plus 1 condition on S1 through Sn, Sn plus 1 condition on S1 through Sn, right? This is the only thing that I have to look for. Okay, but what is Sn plus, which is exponential, independent of everything, right? Do you agree? Is this fine? So now if I use this here, right, in this expression, what do I get? F of, I take this as a homework, essentially the same thing that I showed just some time back, right? Condition on S1 through Sn will be, it doesn't matter, it doesn't depend on anything else, it depends on e to the exponential of minus lambda Sn plus 1 minus Sn, okay? Basically xn plus 1, this is xn plus 1, I can write it as Sn plus 1 minus Sn, okay? Fine. So substitute this. So this results in lambda power n plus 1 e power minus lambda Sn, and this Sn cancels, and you have Sn plus 1. Beautiful, right? Nice result, right?
Yes, sir.
right? So essentially it says, although you are looking at joint density, now you might, any question. So when I write, for example, this thing equals this, what do you say? I mean, is that complete?
No, sir. Divided by some.
No,
And
it is normalized. If you integrate
oh,
this, you'll get, okay. See, remember, you have to integrate it over all, okay, S1, S2, S3, everything, right? Okay, now, okay, now integrate this and tell me that the integral is 1. Otherwise, it's not density and whatever we have proved is incorrect, right? So, can you prove that? Can you prove that when I integrate this, I'll get 1? How do you do that? Anyone? Do you think
Sir,
this is complete? Huh? Yes.
this Sn plus 1 in the expression can be written like x1 plus x2 plus x3 up to xn plus 1.
Correct.
And then e to the power exponential of power, I mean summation. Oh, no.
Okay.
Yeah.
No, okay, let me write the expression, final expression, S1, S2, etc. Sn, S1, S2, etc. Sn equal to lambda n plus 1 e power minus lambda Sn plus 1, 0 less than S1 less than S2 less than and so on less than Sn less than Sn plus 1. This is very important. Okay, so this condition, if you don't have this condition, then this is not even a density, right? If you integrate, you will get infinity. Because of this constraint, when you integrate, you will get 1. See,
Sir,
Sn plus 1.
so
Yes.
this is because of renewal process, right? Definition of renewal process, like the from that we can infer this, that Sn plus 1 greater than Sn.
No, that's by Sn plus 1 is greater than Sn is by definition, right? What is
Yes.
Sn plus 1? It is the n plus 1th arrival instant. How can
Yes.
that be smaller than the nth arrival instant? I mean, you are saying future arrivals is happened before.
Sir, I mean that cannot be, because Sn plus 1 is Sn plus Xn plus 1. Now Xn plus
1 should be greater than 0 almost surely, right? Equal to 0, it's 0. Therefore, Xn plus 1 is greater than 0 almost surely. Therefore, it is true. Is that fine? Hello, Rishabh? Hello? Sumit? Can you
yes,
guys
sir.
hear me? Okay.
Yes, sir.
Okay. Okay, so now I'll state the next, maybe I have 3 minutes. So, okay. Okay, so I won't state it formally. I'll do it in the next class. So if you look at n of t, right, this is the arrival process. I can ask, what is the CDF, or sorry, what is the PMF of this arrival process? So it turns out that this arrival will be lambda times t power n. Lambda is per second how many people arrived. E power minus lambda t over n factorial. Okay, which is nothing but Poisson arrival with rate lambda t. It turns out that this is the expression. We'll see why this is true. The other thing is, if you have an arrival, okay, so for example, there are cars arriving at a junction, and there are 2 roads, okay, one going here and one going here. Now, what the policeman will do is he will toss a coin whenever each car arrives. He will toss a coin. If it is head, he will ask that car to go in this direction. If it is, that is with probability P. Otherwise, he will ask the car to go in this direction. That is with probability 1 - independently of everything. Okay, irrespective of what the car is, what the color is, everything. So he'll just blindly toss and shows. So now a policeman sitting, standing here or here, he will also see an arrival. Okay, suppose this arrival is lambda. This is Poisson with rate lambda. What can you say about the arrival here? It turns out this is also Poisson with arrival rate lambda p. P fraction of the people or the cars went there. The distribution here would be again Poisson with rate lambda times 1 minus p. Okay. Well, you might reverse the process, right? So I can exactly do the opposite. That is, let there is a process, there is an arrival which is Poisson with rate lambda 1 minus p or lambda 1. For example, I can call this as lambda 1 and I can call this as lambda 2. Need not be lambda p. And there is an arrival here. When you look at the combined, both will go in the same road. This will be Poisson with rate lambda 1 plus lambda 2. Okay, the sum. Provided both the arrivals are independent. Okay, it shouldn't be like 100 people here and there, they talk to each other and go at the same time in both the two roads. Then it is not true. But if they are independent, then definitely it's true. Okay, this is another very interesting property about Poisson, which we will discuss in the next class.
Sir, like similar question came in test also, right? Like if X is Poisson distribution, Y is Poisson
Exactly,
distribution.
exactly, right? So you would have already solved that. Yes,
Yeah.
x1 plus x2 is also Poisson with rate lambda 1 plus lambda 2. But we are doing exactly opposite here. We are splitting it. Okay.
Hello, sir.
Yeah. Yes.
Sir, in the above joint distribution, we can find marginal ones, right? By integrating
Which one?
the FS.
Here, right? Yeah, you can find marginals.
So we can describe as each
Yeah,
S1,
so you can
S2,
do
S3
that. So what is the marginal? I have to integrate the joint
overall
e4 minus lambda Sn plus 1 dsn plus 1. But have to integrate over region what? Sn to infinity. Right? Because Sn plus 1 is greater than Sn. You cannot put Sn 0 to infinity, right? So if you do this, what do you get? Lambda n, oh sorry, this is lambda n plus 1. Lambda n plus 1, the integral is lambda Sn plus 1 from Sn to infinity by minus lambda. So what do you get? You get lambda power n. So infinity is 0 and here get e power minus lambda Sn. So you got it, right? What you wanted. Again, 0 less than S1 less than, I should write that. Okay, 0 less than S1 less than and so on less than Sn. Fine? Is that okay?
Yes, sir.
Okay. Praveen, right? Praveen, I can't see the screen. So,
Hello, sir.
yes, Rishabh.
So at the end, where you mentioned the queue, like it will be divided by policeman will toss a coin. So, sir, it is like we are conditioning, right?
You're not conditioning, right? I will blindly, toss a coin. If it is head, I'll ask that person to go to the left, otherwise to the right, something like that.
So then,
Independent.
Sir, actually, the cars were coming from left, so that was following some Poisson arrival process.
Correct.
Right. Then there is a point where a policeman tosses. So that is some extra thing we are adding to the previous process. So, sir, what
No,
it is called?
it's not extra. It's yes, it is extra, but it's independent, right? Independently, I'm doing.
Yeah, independent, yeah.
So that's why the result will also be Poisson.
Okay. Yes, sir. Okay.
It's not like you are tossing a coin and then deciding, well, if it is head and the color is red and this is the fifth arrival, then I'll take it to the left. No, right? It's independent of everything else.
Sir,
That is the reason. Okay, so for those who want to be rigorous, of course, there is a very, very rigorous approach to Poisson arrival. It's called a point process. So those who are interested, you can Google point processes. So there is a rigorous definition for point processes. Poisson processes come under point processes. Okay. Anyway, this will help you understand that definition if you want to be rigorous. For example, Sumit is taking a course in measure theory. So if you want to be that kind of rigorous, then you can look at point processes.
Okay, sir.
Yeah. Fine?
Yes.
Okay. So any questions? If there are no questions, I'll stop. Otherwise, yeah. Any questions?
No, sir.
No? Okay. Any others? Any questions?
No, sir.
So I just wanted to have get a general feedback. What are any feedback on the content, whatever. Okay, let me start with Sumit only. So he's from math background. Let me start by him and go to the next people, the others. So what do you think?
Sir, I
Content is
think
okay, but
everything
I'm.
is fine actually, sir.
Huh?
Sir, the courses are going on fine, but sir, there is some issues like,
Ah.
uh, sir, you used so many terms, so many notation for the same thing. Like, sir, you use something here, and in the next same thing, if you explain the same thing, you just put another notation. So this kind of things are there
Can
for
you give
some
me an
cases.
example? Then it will be helpful.
Yeah, sir, like, sir, when you write, sir, like a PDF or CDF,
Hmm.
sir, no.
Mm-hmm.
So, like here, you just calculate, sir, fx, like, small fx, that is a PDF, and
Mm-hmm.
later you have calculated the probability, like, sir,
Correct.
means
PMF.
directly CDF. Then you said that you have to integrate to get the result PDF, sir, no.
Mm-hmm. No, derivative, right?
So derivative, sorry, sir, yeah.
Hmm. Hmm.
So this kind of things are just confuses, I think.
No, all that I'm saying is you can get PDF by taking, if you differentiate CDF, right?
Yeah, sir. If it is CDF, sir, so we can use here the notation like capital F of H1 is 2, something
So
like this. Then
generally,
we say that, yeah,
this is what we will use, okay? As far as notation is concerned, if I
yeah,
write X or Y or Z capital, that means it's a random variable. That means
yeah.
the
It is a random.
if I
Yeah.
use small, that means it's an instantiation or a variable, okay?
Yes. Okay. Okay.
Okay, so if I use px of something, this is the
Yeah. It
PMF.
is
If I use
PMF. Okay.
f, it's the PDF.
PDF.
Okay.
Yes, sir.
If I use something like this, then it's conditional. Okay, that's all.
Yeah. That's a
So
CDF, sir. For the CDF.
PDF, I'll use fx of something, or I'll
Um,
explicitly write it as probability that x is less than or equal to x. One of the two. Okay.
yeah, sir. One thing more, sir. In some classes, sir,
Ah.
you just move very fast. I think, sir.
It just stop me, no. So we say, hold on. I didn't understand. You can stop me. No, don't hesitate, huh? So, by the way, this is
Okay.
what I'm going to stick throughout the stick to
Course,
throughout
okay,
the
sir.
course. Okay.
Yes.
Others, Ayush.
Yes, sir. And everything is, sir, okay, I think.
Okay. Okay. Ayush, quickly. Yeah.
Okay, sir.
Fine. Okay.
Fine.
Rishabh.
Sir, I will also say the first chapter was very vast. So I have some kind of difficulty like digesting all those theorems. But
Okay.
now in coming to Poisson process, like second chapter, now it's kind of stabilizing.
So the idea is you can talk to Savan also. Last time, I think 90% of the course was first chapter. I mean, I did
Sir,
much more
actually,
than
sir,
that.
it's very vast. The first chapter is like so many theorems and so many concepts are put together in like 12 or 13 lectures. So
Correct.
yeah.
Yeah. So if you have any questions, you can come back to me. We can discuss.
Sure, sir, sure.
Okay. Yeah. Not many. I mean, see, there are notions of convergences. That is something that you should know. Central limit theorem is another. I think pretty much that those are the important things. I mean, we will kind of use that later on. But otherwise, the remaining things were from undergrad, almost from undergrad.
Yes, sir.
Anyway, so if you have any issues, questions, concerns, we can discuss. Okay, so who else? Praveen.
Yes, sir. It's fine, sir. But I need
Ah,
to go through once the book, the textbook, sir.
you should go through, man. So you should
Yeah,
not.
no, sir, no. Yeah.
Okay. Fine. Jayant.
It's fine, sir.
Fine. Did I miss anyone? Lokesh. Lokesh is there, right? He's
Not in
credited.
this class, sir.
Huh?
He's not in this class.
Lokesh is not in this class. Okay.
No, he's data science. He's undergrad.
So
No,
Nitish.
no. Nitish.
Nitish.
Sorry.
Nitish, sir.
Nitish. CS, right? Yeah.
He's not there right now.
Nitish is not there.
No.
You wrote the test or?
Yeah, he wrote it.
Okay.
Sir, if you can give any examples related to communication, that would be nice, no, sir? From now on.
Yeah, so for example, the number of packets arriving at a
Yeah,
queue or a router,
yes, sir.
that is boson, right? So I mean, I cannot say much more than that. Then it will
No,
become
no,
a
no.
computer networks course, right?
Yes, okay, sir.
Yeah. So this is, you can think of it as just don't just stick to communications that way. Keep it general so that you have a general understanding, but in terms of applications, when you look at communications in particular, you can apply this tool there. Okay.
Yes, sir.
Okay. Whenever possible, I'll keep it general, but I'll also, if you are interested, you can ask questions. I can answer from a communications viewpoint. Okay.
Okay, sir.
Okay. So anything else? If not, I'll stop here.
Sir,
Huh.
I have a doubt regarding applying Leibniz rule, sir. To means if the upper limit is or the lower limit is minus infinity or plus infinity,
Okay.
then can we apply Leibniz rule, sir? Is there a, or should the upper bound and the upper limit and the lower limit should be finite?
No, Leibniz meaning you are saying
So integration, like differentiation.
Differentiation of integral.
okay, so you are taking differentiation of, let's say, x integral, let's say x to infinity something, right?
Yes, sir.
These kind of
T,
things. Okay,
T
what do you
comma x.
want?
Yeah.
Huh?
Yes, sir.
No, not t comma
Can
x.
can we apply Leibniz rule for this type of?
Yeah, I can see this, right? So what is derivative? It's x plus some epsilon to infinity g of t dt minus, is that correct? No, it should be the other way. Okay, x to infinity, then minus x plus epsilon to infinity g of t dt. Okay, so by epsilon, right? This is what, and you take the limit of this. That's how you find the derivative. So what is this? This is 1 by epsilon x to infinity, x plus epsilon to infinity. This would be x to x plus epsilon g of t dt, right? Now you can, so this goes to, for example, g of x. When will this go to g
Epsilon
of
tending
x?
to 0.
So first of all, this integral should exist. Of course, it exists, right? And then, what is that? You were saying something. Hello? Hello?
Praveen said something. So no, I did not say anything.
Praveen, you were saying something?
So I said epsilon tending to 0.
Yeah. So as epsilon goes to 0, now the question would be whether it goes to g of x or not, right? If it goes, the limit should exist. That's all, right? When will the limit exist? See, this I can, it depends on what g of x. So you have x here and x plus epsilon here, let's say. Okay, this is your function. Okay, let me write it slightly. Okay, this is your function. Okay, of course you are making epsilon really small, right? This is what you are finding the Riemann integral, let's say. Okay, the usual integration.
So like there
Now,
should be any discontinuity or like that type of on GT.
so let's see. So for example, what is it that you are doing? So if this integral, I can do two things, right? So I can find the maximum of this g of t in this interval and minimum of this d of t in this interval, and upper bound this by max overall t in that interval. Okay, whatever the small interval I epsilon is of g of t times epsilon, right? Okay, is that fine? And then this is upper bounded by this, but this is greater than or equal to, I can find the minimum overall epsilon in the interval g of t times epsilon again, right? This will be your integral. Okay, now I'm dividing by epsilon on both all the sides and taking epsilon to 0, right? So this goes to 0, this goes to 0. Now the limit exists if both these two are the same, right?
Yes.
Yeah. So that
So
means
it totally depends on g of x.
exactly. So at point x, right? So when you take, for example, x here, and you take some sequence that tends take that limit or a small interval around it, the max and the min, right? As you shrink the interval, it should go down to 0. Sorry, it should go down to the same value, or the max min difference should go down to 0. That means what? It should be smooth, right? Do you agree?
So smooth means there will not be any discontinuity, or
Yeah, exactly, right? So, for example, this is your x, this is your function, okay? Okay. Now what happens? You take a small interval, right? What is happening? The min is this value, right? Let me call this as a and this is b. A less than or equal to something is less than or equal to a epsilon is less than or equal to, this will be b epsilon, right? Even if you shrink epsilon to 0, right? No matter what, it's still b epsilon is the upper bound, a epsilon is the lower bound, a not equal to b, so it doesn't converge, therefore you cannot apply Lipschitz. Sorry, Leibniz.
yes, sir.
Okay. So this is called analysis, right? It's a thought process. You just see what is the condition. Well, by the way, I didn't remember these things. Okay, so I just came up with this.
Sir, in the test, in the quiz, sir, there was a problem. The first question, no, sir. There we have to apply this one. So there the modulus of x minus some alpha, I think, or c, I think. So
modulus is fine. It's a nice function.
Yeah, sir. So there is a two part. We have to just divide the R into two parts, no, sir. Like x is greater than c and x is less than c.
Okay.
And in those two subintervals, these functions are smooth functions. These two are. So then we can easily apply the Leibniz rule, I think.
Correct.
By the formula only.
So in the test, right? I mean, if you are stuck with that kind of a thing, one thing is, I don't know if I should say this. Generally, things are nice in tests. Okay, so that means you can apply Leibniz.
Okay.
Okay, that is something that we can assume and clearly state. Applying, assuming that the function is nice and all that. Okay, so at least that shows that you are thinking in the right direction. I mean, you are thinking rigorously. Maybe the function itself is not nice. Still, I will give you points because you are assuming something and went ahead and everything else is correct, but the starting point where you assume that it's incorrect, the things are not smooth. You have assumed that it's smooth. That's where I'll probably remove some marks. But otherwise, everything will be fine. Okay. It's a thought process, right? Even in when you do research, that's what you do. But of course, you will also verify whether things are smooth.
Yes, sir. Okay.
Okay. Yeah. Well, if you want to be rigorous here, you replace max with soup and min with the in. Okay, that's what you have to do. Okay. So, any other questions?
No, sir.
Okay. Yeah. Yeah. It's fine. Okay. Okay. So I'll stop here and we'll meet tomorrow. Okay.
Okay, sir. Thank you, sir.
Okay, sir.
Yeah, thank you. Bye.